Okay, let's get started. So let me do the following. So today I want to first start by wrapping up this discussion of soft theorems. Right, we wrote down briefly what it looks like for dilation symmetry, um, but there are many comments to make. So this is from yesterday. Just to remind you, we basically say the following. Under this, there is a non-zero transformation on zeta, and it has a linear part and the nonlinear part. I'm just going to write down the nonlinear part. The nonlinear part, it just shifts zeta by a constant, right? And from that, we derive a consistency relation or a soft theorem, which is often called consistency relation in cosmology, and it has this kind of form. From now on, for the rest of today, when I write Q, I mean the soft momentum. So Q is the soft momentum. This kind of correlator, where this O is some observable, and it might have many high K modes. I'm just being lazy and just write it all as K, right? So this is some observable, involving high K. And usually not just one K, but several, but I will just write it as K schematically. And it turns out we write down a relation of this sort, that this is roughly equal to the transformation of this observable. Is a relation of this sort. So therefore, let's say here there are n hard momenta multiplied together. So let's say, suppose this is an n-point function. Then on the left-hand side, this is an n plus 1 point function. I hope that is clear, because you have this additional soft zeta mode floating around. And this is the general structure of these soft theorems of consistency relations. It relates an n-point function to an n plus 1 point function, where the additional one is very soft. So the example that we did yesterday was this was a 2-point function with momenta k1 and k2. And then on the left-hand side would be a 3-point function with momentum q, k1 and k2. And by momentum conservation, you know, if I do a 3-point function that involves 1q and 2k, k1 and k2, the momenta has to sum to 0. And so you usually represent by saying, oh, I have some kind of triangle. That's k1, k2, and q. And you are taking the limit. That q is very, very soft. So in momentum space, q is very, very small. And people usually call this kind of configuration a squeeze configuration. It's like you're squeezing the triangle. So the soft limit is the same as the squeeze limit. So people would say, I'm looking at a squeeze 3-point function. That would be the soft limit. Okay? So this is what we this is where more or less where we stopped yesterday, right? And now I have a number of comments about this. Any questions before we start there? Yes, Max. You mean this observable, can it also contain soft modes? That's what you're asking. Or what? Yeah, multiple ones. So for example, the example we work out, this O is also constructed out of zeta, but you don't have to. For example, let me give you an example. This zeta is basically like some kind of gravitational potential. It lives in the metric. This is observable. I can just say, well, I'll just use temperature in the sky, temperature, or I use the galaxy density in the universe, density, which is not actually zeta, but in the end, it will be related to zeta somehow, because in the end, the metric is always coupled to the matter fluctuations. But I think the point I want to make is this observable can be very general. It doesn't have to be just products of zeta. Yeah. Hiju. Yeah, you can actually derive, that's one method for deriving the soft theorems is to use OPE. I did not do that yesterday, but it's certainly one method. Yeah. Other questions? Well, yes. Yeah, that's one of the comments now. Okay, so let me make a number of comments. Actually, before I raise this board, so my comment number one is the following. If you think about what we did yesterday, this is a transformation on the observable. In the case where the observable is a two-point function, I argue that you actually only need to keep the linear part of the transformation and forget about the nonlinear part, because you get a one-point function which is 0. It turns out the following is true, which I'm not proving. If on the left-hand side you confine yourself to connected part of whatever n plus 1 point function you have, this is the C for connected part. Then on the right-hand side, it turns out you can show by induction it's okay to just do the linear part of the transformation and completely forget about the nonlinear part. You got that? That's my comment number one. Yes? So let me write it down here. So I have a number of comments, in fact, quite a number. So if the left-hand side is a connected n plus 1 point function, then the right-hand side, you only need to do the linear part of the transformation. Okay, and I'm not showing it, I'm claiming it. Maybe at the end I'll give you some reference so that you know where to look. Okay, but that's my comment number one. Yeah. Are connected. So are connected. Let me do a 4-point function. So for example, if I do 4 things, I can compute a 4-point function like that. When I say connected part, what do I mean? I basically mean this. The connected part is the same as these 4 guys minus these, but because this is 1, 2, 3, 4, this is 1, 2, 3, 4, there are actually 3 permutations plus 2 other permutations. And you can generalize this to any point. Does that make sense? That's what we mean by connected. Yes?
What if you have a subset of connected diagrams, like just one PI, for example?
A subset of connected diagrams. Well, here what I'm saying is I'm not doing diagrammatics in the sense of perturbation theory. When I say connected correlation function, it really does just mean this way, meaning the following. Give me a Gaussian random field. Maybe you have seen this. Let me explain it as follows. Suppose I give you a probability distribution for a single variable x, and it's a Gaussian. Suppose I tell you that. Yeah? The mean is 0. The variance is not. And the variance would be related to this, whatever this exponent is. In fact, I'm going to write it this way, 1 over 2 over sigma square. Then the variance would be sigma square, right? All the odd moments, x to the odd power, would be 0, as you might expect. And then how about the even power? E to the 2n. I don't know whether you have seen this before, but this is some kind of Wick's theorem if you want. So you say, I can compute this. If you feel powerful enough, you can compute it. And it will always goes like x squared to the nth power times something. Yeah? And this is the general structure for a Gaussian distribution. The point of defining connected moments or connected correlation function is to subtract off the Gaussian part, basically. So this looks like a 2n correlation function. You just subtract off the Gaussian expectation. The leftover is what we call connected. So it's a definition of what we call connected moments or connected correlation function. Does that make sense? Yeah? Other questions? So second comment I want to make is that as Will asked earlier, the dilation symmetry actually is not the only one. So dilation, in fact, I already noticed a mistake. You should have corrected me. When I say dilation, of course, there's an x here. Yeah? Right? I'm scaling x. So there's an x here. This is a constant. So dilation look like that. X goes as x minus lambda x. Zeta goes as zeta minus lambda. I'm just showing you the nonlinear part. It turns out there is special conformal transformation. Conformal transformation, which is also a residual diff that you can do, it turns out. I'm not showing you, but you can show it. And the structure is basically x going to x plus some number times something that goes at x squared. So this goes as x, this goes at x squared. And then the nonlinear part of zeta, let me write this way. Delta nonlinear zeta, it was a constant before, but for SCT, now this goes as some number times x. You see what I mean? You just raise the power in x from dilation to special conformal in both the diff and the nonlinear part of the transformation. It turns out this is also a good symmetry. It's, again, one of these large gauge transformations that you could do in the unitary gauge that we happen to pick. This is still good. Okay? And then perhaps surprisingly, or maybe not so surprisingly, you can keep going. The higher ones, meaning x to some higher power, x cubed, for example, where this delta nonlinear zeta would go as x squared. The higher ones, these higher ones, involve both zeta and the graviton, the tensor mode, zeta and gamma, and I'm not going to write it down. But it turns out it just keeps going. Okay. And so for each of them, you will write down a consistency relation of the form that I wrote down, but the soft theorem. So for example, let me just do this one. The soft theorem, it would look like something like this. P zeta Q delta linear Q of the observable This would what the dilation one looks like, which is already what I wrote up there. The special conformal mode, because it involves an extra power of x, it becomes an extra derivative with respect to q on the left hand side, basically. And the higher ones would be, the next one would be second derivative with respect to q, and so on, basically. You got it? But the higher ones would actually involve a soft graviton as well, a soft tensor mode, and a soft scalar mode. Okay, I'm being very schematic here. Yeah. It involves both quantities. The scalar to tensor ratio, I would say, is already what we derive just using basically the the free part of the theory, right? You might remember. But these kind of symmetries, they do tell you that if you do some of these higher transformation, they are associated not only with a very soft scalar mode, they are also associated with a soft graviton mode, a tensor mode. You have to actually include both. Yeah. Am I answering your question? Or do you yes. Yeah, that's right. The way you should think about these extra statement, let me just not be completely vague here. Basically, these extra soft theorems, they look like this. This is Q, this is Q, and then there is a soft gamma, the graviton, the tensor mode. Is of this form, but it is requires taking higher derivatives of this. This is the form, schematic form of these higher ones. That's what they look like. Yeah. Okay. Yes.
Those higher order transformations that you are talking about, are they calculation of SCT and dilation, for example, or are we talking about theories which are even more symmetrical?
Beyond. So these higher ones, for example, the next one would be x goes to x plus something to x cubed, not x squared. So it's not SCT, it's something else. Yes. Yeah, it turns out the way you derive this is you basically again ask yourself, what are the large gauge transformation I can do that leave myself in the same unitary gauge, and you make one assumption. You assume the tensor mode is very small, so you are going to do it perturbatively in powers of the tensor mode. And if you do that, order by order, there would be one of each of these that you can write down systematically, and they all produce something that schematically looks like this, soft theorem that look like this. Yes. Okay, good. This is completely non-perturbative. This one already, this one I would say is also non-perturbative. These ones are in some sense expanding. These ones involve expanding in powers of zeta. Sorry, in power of gamma. So I would say they are more approximate than these ones. with the understanding that somehow, and that seems to be the feature of our universe, that the tensor mode is somewhat suppressed compared to the scalar mode, right? You might already know the tensor to scalar ratio these days, the bound is about percent, a few percent or less. So that's what is used here in writing down these statements. Okay, but let me not dwell on these higher order ones too much. What I want to do is to give you some idea how to connect this with this symmetry breaking, spontaneous symmetry breaking. And let me remind you this. So this is my comment number 3. Do you remember yesterday when we derived this, where does this term come from? Just go back, try to recall our derivation yesterday. This term, recall, this kind of term comes from variation of the wave functional. Do you remember this? You are changing the wave functional, and from that it pulls out a soft zeta, and that's really where this soft zeta comes from. And the fact that that is true, it basically tells you something interesting. This symmetry transformation actually changes your vacuum. Remember, the wave functional is the vacuum wave functional. The fact that this is non-zero, it tells you, the fact that this is not actually equal to 0, tells you the symmetry is in fact spontaneously broken. In fact, very often we use the two terms basically interchangeably, you know, non-linearly realized symmetry, spontaneously broken symmetries. We basically use those two terms interchangeably. And here, conceptually, you should just remember the way we derive this is actually by thinking carefully about how the wave functional, the vacuum wave functional is transformed, which means this symmetry actually changes your vacuum, which means your vacuum actually spontaneously breaks this symmetry. So to give you some rough idea, I want to recall the simplest example of one of the simplest example of spontaneous symmetry breaking that you probably have seen, right? You have this Mexican head potential for some complex scalar, right? And you have a U1 symmetry, and your vacuum can be anywhere along this circle. Those are the possible minima that you can pick, and you just pick one. You say, this is my vacuum. Yes, you say this is my vacuum, but once you pick this as your vacuum, your choice have broken this U1 symmetry, and that's why we call this spontaneous breaking of the U1 symmetry that you started with in your theory, right? So the choice of the vacuum represent a spontaneous breaking of this U1 symmetry. And as you might know, even though your symmetry is spontaneously broken by your vacuum, somehow this symmetry still exists, is out there, it has physical consequence, and you know what the physical consequence is, right? The physical consequence is Goldstone modes, right? So there are fluctuations that are massless, that go around in the angular direction. Those are the Goldstone modes. So yes, your symmetry is spontaneously broken by your choice of the vacuum, but the physics still knows about the existence of this U1, and it manifests itself in the existence of Goldstone modes, massless degrees of freedom that allow you to go basically along basically this angular direction. And essentially, the way you think about is this soft zeta that we talk about is basically a Goldstone. And so the soft theorems, you can also say is a soft Goldstone. theorem. And sometimes you hear people say solve pion theorems, because as you might know, we like to think of the pion as some kind of goldstone. So people might say solve pion theorems, basically meaning the same thing. Okay? So this zeta is basically a goldstone. I think that's an important conceptual point. Any questions about that? Let me bring this even more down to earth by talking about the Newtonian example. So then you will see what I'm saying actually is actually just very simple. So think about the Newtonian example. This as a gravitational potential, I'll write this way. As you know, as we discussed maybe 2 lectures ago, the Newtonian gravitational potential, you can shift by a constant and the physics does not change. So clearly it's a symmetry. Yes? You would say this. You can shift by a constant and clearly it's a symmetry. And the fact that looks like this symmetry is also non-linearly realized tells you there's some sense in which you can think of the Newtonian gravitational potential as a goldstone. You see what I mean? It's like a goldstone. And in fact, as we discussed, the correct statement about correlation function that involve the gravitational potential is not that it is invariant under shift. Clearly, this is not true, as we discussed 2 lectures ago. The correct statement turns out to be that there will be some soft theorem associated with the gravitational potential. The fact that this is a symmetry of the dynamics for sure. So instead of this, instead of saying we have invariant correlation function under phi go to phi plus a constant, we have soft theorem for phi correlation functions. Okay. Let's dwell on this just a little bit more. So when I say somehow there is spontaneous breaking, well, what do I mean by spontaneous breaking of whatever states that I have in mind here that somehow breaks this shift symmetry? What am I talking about? I'm talking about something actually very mundane. Imagine you do just classical mechanics, you solve for the gravitational potential sourced by the Earth, for example. We usually say, well, it's minus gm over r, right? But there's always some ambiguity about that overall constant. And usually we say, well, I'm going to just choose the constant so that the gravitational potential goes to 0 at infinity. Usually that's the way we define that constant or choose that constant. That very choice means you have chosen a vacuum. Meaning that very choice is saying, among all the possible vacuums you have chosen, I am now going to choose one, and that one just corresponds to the usual boundary condition that the gravitational potential goes to 0 at infinity. You see what I mean? You have now make that choice. And because you make that choice, now the shift symmetry, this symmetry is spontaneously broken. Yes? And therefore, for that reason, correlation function of the gravitational potential cannot mean this side is equal to that side. They are obviously unequal. And let's deduce the correct statement. So suppose I have this, and let's just do phi k1, k2 divided by p phi q. Somebody tells me, so if I take the limit q go to 0, just by analogy, with what we have been saying about zeta, what would you say this should be? What is on the right-hand side? What is on the right-hand side? In particular, keeping in mind what I told you, that as long as you talk about connected moment, it turns out on the right-hand side, the only thing you need to do is to look at the linear part of the transformation. So this is now my observable. Tell me, somebody tells me, what is the right-hand side? What do you think? Just make a guess. It's 0, yes. Very simple guess. This is just 0. Yes? Because the shift symmetry on the gravitational potential is so simple. There's no linear part of the transformation anyway. So this is just 0. That's the statement. Now let me expand this statement a little bit more. This statement means behind it, let me pretend Q is actually not quite at 0, it's just very small. When I say it's 0, here is what it could mean. It could mean basically that it starts at something that is proportional to Q, and then when you take Q to 0, then the right-hand side goes to 0. And if you think of this as a power series as soft momentum, probably it would go like that. That's really what it means. But the important point is the Q to the 0 term cannot be there. That's what we mean when we say, oh, the right-hand side has to be 0 in the soft limit. And when I say the Q is small, you should think of this as the ratio of Q and K. So basically, you should think of this as kind of a power series expansion of Q over K. So that's what we mean. So you observationally find a way to measure this 3-point function divided by the 2-point function. Of course, your measurements is always at some finite Q. The Q is actually not 0. You measure always have some finite wavelength, right? But you check the squeeze limit, Q, K1, K2. You check the squeeze limit, and then you ask yourself, as I approach this limit, do I find something like this or not? Or do I find, no, it has to start at this order in Q? That's basically the check you want to check. And again, the fact that you can make this kind of statement for finite Q is because you have used some kind of adiabatic mode condition to make sure whatever statement you derive here is smoothly connected to physical modes. Even though, strictly speaking, the symmetry that you are using is a gauge symmetry. That tells you something about Q equals 0. Okay? So that's my fourth comment about this. Any questions? The Goldstone boson is the gravitational potential itself. Yeah, this is the soft Goldstone. Yes, usually we don't think of the gravitational potential as a Goldstone, but really it does play the role of a Goldstone in this particular case. And you can. That's right. Let me turn this into something that's actually even closer to observations. Those of you who do large-scale structure, you know, usually we don't measure endpoint function of the gravitational potential. We measure endpoint function of the density, usually, yeah? And so usually you measure density. And how is density related to potential? How are they related? They're related by Poisson's equation, yes? So in Fourier space, you would say Laplacian phi, which is q squared times phi of q, is, I'm just dropping constants, is of the order of the density fluctuation at the same momentum q. No, that's what you would do. This is Poisson equation. Yeah? You agree? And so instead of this statement, perhaps a statement that's more directly related to what you actually measure would be a statement of the following form. You say, I hope you can kind of see it. It's just saying, well, instead of doing this, I can do this. Yeah? And this has to be related to this by just some powers of q, no? Because phi and delta are just related by q squared. And I hope you can work that out in your head. The left-hand side of that equation is just this times q squared. Why? Because this delta q is q squared phi. This power spectrum involves 2 delta. And so this is roughly phi itself has q to the, this would be q to the 4th because q squared here. And so at the end of the day, the left-hand side over there has to be matched by this. And so the claim is this has to be equal to no q to the 0 term. It has to start with order q plus q squared and so on. That's the statement. Or if I take this q squared and now move it to the right-hand side, I can rewrite this delta q, delta k1, delta k2 over the power spectrum of delta q has to be equal to, this term cannot be there, you divide by q squared. The next term is potentially there. And then the next term is also potentially there. And write down that way. No, I just divide overall by q squared. So another way to say the soft theorem for large-scale structure is, if you measure the density 3-point function divided by the 2-point function, take the squeeze limit, it cannot have a 1 over q squared pole. You understand what I'm saying? So you go ahead and in your data, you measure this triangle. Again, all our measurements is never at q exactly equal to 0. You can just take the limit q smaller and smaller compared to k. And then you ask yourself, is there any sign this combination of 3 and 2-point function looks like it's blowing up as you take the squeeze limit? Blow up in what way? 1 over q squared. And the soft theorem tells you that no, you should not have that 1 over q squared pole. Does that make sense? Any questions? Yeah, Hidru.
Let's suppose that we have measured the transformation function and we have found that there is actually a pole making up the
Mm-hmm.
We mean that the assumption that we made that the gravitation is solely conducted by what is the cosmology.
Yeah, basically we will be testing that the initial condition is basically driven by one single degree of freedom, like a single inflaton. We'll say more about that. What are we testing? When we are trying to check, does the data have a 1 over q squared pole or not? We are basically testing that assumption. I'll write more about that in a moment. But let me wrap up what I want to say by saying the following. It looks like then this symmetry, which is shifting the potential by a constant, tells you that there's no 1 over q squared pole, but it looks like potentially allows a 1 over q pole. It turns out there is an additional symmetries that you can write down, which involve shifting the gravity potential not by a constant, but by a linear gradient. Imagine you have a gravity potential which is pure linear in x. That looks like, what does that look like? The gradient of phi, which is the gravitational acceleration, looks like a constant, no? A constant gravitational acceleration. And a constant acceleration, gravitational acceleration, you know what that means, no? If you go into the freely falling frame, you can cancel that out. Basically, that's the idea. So there is a higher symmetry where this is shifted by a linear gradient, and it turns out if you use that, you also zero this out. And so it has to start here. Okay? That's the statement for large-scale structure. And is Angelo here? Yes, left. Well, Angelo is there. So Angelo actually has actually checked this in simulations. So Angelo use a suite of n-body simulations, measure this. The n-body simulation start from Gaussian initial condition, small perturbation, and let the perturbation grow under gravity. And then he checked, is that this pole? No. Is that this pole? No. And the important thing about that check is, in the simulations, he's going to triangle where these K1 and K2 are actually in the nonlinear regime. So he's doing a check that's beyond perturbation theory. And it works. So if you start from those initial conditions, these two poles cannot be there. Okay? And so it's kind of a reassuring thing, because the claim is these theorems are fairly robust. We are not doing perturbation theory. It's just a result of symmetry. And in that sense, it should work regardless of whether these hard momentum modes, small scale modes, even if they are in the nonlinear regime, it should still work. Yeah? And let me just add one more comment on that note. The statement actually, I can make it even stronger. Not only is this robust when this is in the nonlinear regime, this is robust even if these observables are something else, right? Including, for example, I don't have to do delta of the mass. I could do delta of the galaxies. I put a G here, which is really what we observe. We measure galaxy clustering, right? That's the things that we can measure. And the claim is, if you do that, this statement would still work. And as you know, galaxy formation can be complicated, and it's hard to work out from first principle because star formation and the aftermath of supernova explosion, driving out gas, and so on, is a complicated process. So it's hard to predict very reliably, especially on small scale, what's the galaxy clustering. But what this is telling you is, at least this kind of statement, in the presence of a soft mode, that is the main caveat, you can still reliably say that this pole should not be there. So it allows you a way to use data. In large scale structure, we actually have very good data on small scales because there's so many high K modes in your cosmological or galaxy survey volume. So you have very small error bars, actually. However, we usually feel shy about deriving cosmology from those very high K modes because we cannot very reliably predict the galaxy clustering at high K. And so these kind of statements, which we feel relatively confident about, even if these are at high K and these are galaxy observable, from that point of view, is useful. It's useful to have. Any questions about what I just said? No? Yes, there you go, yes.
Do you have in mind any example in which you can make one of the two square poles?
Yeah. So Angelo has also looked at simulations where the initial condition is designed to actually produce this pole. So let me tell you about that now. Because at the end of the day, it's all nice and good to say this is robust, but in the end, after you measure it and check it's not there, what do you learn, right? So you want to know what do you learn. So let me talk about that. What can we learn? And so this is my comment. I don't know. I think I've made many comments. Maybe comment number 5. My comment number 5 is this. The form of the soft theorem actually is model dependent. It has model assumptions. So the form of the soft theorem can be modified if you deviate from single field slow roll inflation. Let me amplify on that note. So remember yesterday we talked about this picture that I have this potential, this is the inflaton potential, this is the phi inflaton, this is the potential thereof. And I have the inflaton sitting here and it's slowly rolling downhill. And we say, well, imagine you have this and now coupled to gravity, right? Remember that? And then we say, we're going to use the inflaton trajectory as a clock. Yeah. We chose unitary gauge to zero out any spatial fluctuation in inflaton, but I don't have to. In fact, physically, it might be helpful to think about the opposite. I'm going to imagine I use a gauge where zeta is 0. So all the fluctuation interesting is actually lives in the inflaton now. Yeah. And what is the inflaton doing in different parts of the universe? So in one part of the universe, the inflaton might be rolling down the hill here. In another part of the universe, the inflaton might be rolling down the hill here. You understand what I'm saying? So they have different rate of progress of rolling down the hill, basically, in different part of the universe. And once again, this inflaton, in some sense, is controlling the clock, because then depending on your rate of progress, this different part of the universe now is going to have the inflation end at basically different times, yes? The local physics of how the inflaton, at the end of the day, all the energy get dumped into producing all the standard model particles that we like. That process is determined by the local physics of the coupling of the inflaton to, let's say, the standard model particles, photons, and so on. So that process is universal. The only difference between here and there is basically the fact that this part of the universe, inflation ends maybe earlier than this part. But the physics, the local physics of each of these patches is exactly the same. And so in the inflation picture, basically, there's only one fluctuation overall that controls everything. Yeah, so in this part of the universe, maybe because inflation ends earlier, you inflate less, so maybe you produce, at the end of the day, less density of particles compared to over here, yeah? But in each patch, the ratio of different kinds of particles, photons, neutrinos, what have you, that's the same, yes? That's the only fluctuation is this overall kind of fluctuation of the inflaton clock. And that's what we call single field. So it's single field kind of initial condition. To the extent that is true, then this consistency relation works. But if you deviate from that, which is not hard to imagine to deviate, there are other fields that are important. Then you would break this form of the soft theorems If you insist on thinking about soft theorems, you will have to rederive your soft theorems, and there will be corrections to these. And so checking this form of the consistency relation or the soft theorem is checking basically single field slow row. And one thing we did to answer Diego's earlier question was we chose initial condition in this suite of n-body simulation that does not correspond to the normal single field slow row. It's a model called local FNL non-Gaussianity. I don't know whether that makes any sense to you. I'm not going to explain it, but anyway, in those simulations, Angelo can repeat, he did repeat his measurements, and he find 1/q squared pole. And the size, this coefficient, basically measured a particular parameter in that kind of initial condition, and it's called local FNL. And you can basically think of applying this to data, looking for the coefficient of this pole as a measurement of local FNL, basically, or as a bound on that quantity. So that's the idea. That's the idea. So that's my comment number 5. I think I see I have too many comments. Do I have? Yes, please. It will be different. So let's say you have axion isocurvature perturbations. Let's say, and the axion is really the dark matter, and so that fluctuation is a completely different source of fluctuations from basically this inflaton-driven clock. So once you have that, you should actually you would have to rederive your soft theorem if you want to think about soft theorems, and there will be corrections, and I'm not completely sure that the result will be as dramatic as creating a 1/q squared pole. It's probably going to be different. They are what? Yes.
They can't show up.
That's right. That's right. That's right. That's right. So, yeah, basically any additional light degree of freedom that somehow leaf is imprint in large scale structure today, that is going to modify this. Yes. Okay. Very good. Let me make one last comment. No, was there another hand? No. Let me make one last comment. The fact that this soft theorem originates from gauge symmetry, I have to say, is a source of a lot of confusion. So you would sometimes hear people say, oh, the soft theorem of consistency ratio is unobservable because it comes from a gauge symmetry. And I would say those statements that sometimes you can find in the literature, I would say is a bit misleading. So let me phrase it as follows. The fact that we have used adiabatic mode condition to derive the soft theorems basically tells you you are in the end making some physical statement about observable things. For example, the 3-point function of the density, does it have a 1/q squared pole or not? So it's a physically meaningful statement that you can go and check. And in fact, the fact that we can run simulations and check it tells you it's actually pretty physical. Nonetheless, it is true. I can tell you the origin of some of the statement in the literature is that these soft theorems, the soft theorem, if you choose the right fields, instead of basically this one, which is what I told you, just by being clever about your choice of actually what is the field that go in here, or more accurate, what are the coordinates you are using. Instead of this, you can transform it into something else. Let me put a tilde on top, because you are using a different definition. where the right-hand side is 0. That is certainly true. So when you sometimes hear people say the consistency relation is unobservable, this is actually what they mean. You can choose clever choice of quantities such that there's no right-hand side. Yes, that is definitely true. But the fact that it has physical meaning should be kept in mind. And is the simplest way to argue that physical meaning is the following. Something that is pure gauge, has no physical meaning, can never be violated. The fact that it can be violated, that you can come up with models that produce this 1/q square pole, is kind of the most, make it so, the most manifest or explicit way to show these statements have physical content. Yeah, and so don't be misled by those statements. Sometimes you can hear people talk about this. This is a gauge symmetry. This is really a pure gauge. It has no physical meaning. The fact that you can violate it tells you it has physical meaning. Okay, so I'll just leave you with that comment. I think that's it. That's all I'm going to say about soft theorems. Any questions? Yeah. Yeah. Yes. Good. So I was invoking one particular example of a large gauge transformation dilation, but it turns out there are many more you can write down. So the next one, another large gauge transformation, which go at a higher power in X, is this special conformal transformation. And then it turns out if you expand in powers of the tensor mode, you can keep going. There's actually an infinite number. Does that answer your question? We have fixed all the small gauge, meaning all the diffs, the space and time diffs, we have fixed it to the degree that now if you are only interested in transformation that actually vanish at infinity, is completely fixed. But for the ones that are actually can blow up or does not go to 0 infinity, there's still a lot of freedom left. Yeah. I mean, if you like, if all this sounds a bit abstract, think about E&M. You know, E&M, you have U1 gauge symmetry, but there's something that we call the global part. The global part is just the U1, a constant, right? When you have charges around, that actually does something for you, and in fact, you use that global U1 to deduce that charge conservation for the charges. So think of it as and what we are talking about, think of it as an analog of that. So I have a question for you. We are now at noon. We can either start talking about black holes. That's one option. The other option is I feel somewhat obligated when we talk about soft theorems to at least tell you something about what soft theorems actually looks like for amplitudes. In particular, talk about the Weinberg soft theorems for amplitudes. So any preference? I can tell you about that before I talk about black holes, or we'll just forget about that and go straight into black holes. Let's do a show of hands. Who wants to hear about Weinberg soft theorems? Okay. Who doesn't want to hear about Weinberg soft theorems? Luca, you don't want to hear about it because you know it already. Michele doesn't want to hear it because Michele already know. Okay, I will try to make it brief, okay? But I feel guilty not to at least mention it since we are on the subject of soft theorems. So soft theorem for amplitudes, right? So what do we mean? So suppose I have some process, some amplitude, and it can involve many particles, but let's say one of the particle is very soft, right? So again, I'm going to use Q to represent the soft momentum. Very often in a lot of theories, not all theories, but in a lot of theories, what you find when you take the soft limit, this goes as Q to some power. Yeah, that power depends on your theory. So let me do something very simple. So example, suppose you have a theory that is shift symmetric, and the only interaction you have, let me do the quartic interaction. The interaction is d phi to the fourth. So phi, I keep writing phi, but don't confuse the different phi, right? This phi is just some generic phi. If you have d phi to the fourth as your quartic interaction, suppose you go ahead and compute 2 to 2 scattering amplitude, 2 to 2 scattering, and one of the leg is soft Q. I hope you can see what is that power. Just guess what's that power for that theory. 1, no? It will be 1. So this exponent will be 1 for that theory. And you can imagine that for different theories, you will get different exponent. That's not surprising. And there's some scalar theories that are kind of have curious exponent, meaning they have extra powers, not just Q to the 1, but higher powers. And it's because of additional symmetries beyond just shift symmetries. I'm not going to talk about that. I'm now going to talk about now amplitudes that involve gauge, the gauge boson, namely the photon and the graviton, right? So that's the Weinberg soft theorems. So Weinberg. Okay. And the idea is the following. Suppose you have some complicated process. It doesn't even have to be 2 to 2. It can be many. Yeah? And these are all, let me call this momentum K. So for example, this K1, this K2, K3, and so on. All the way to, let's say, yeah, as many as you want, okay? All this K. And now I want to call this process. I'm just going to abstractly call this process is the amplitude. Let me use A. Is the amplitude from some state alpha to some state beta. So I will just say alpha to beta. That amplitude. Now suppose I'm interested in the same process, but now this same process involves the emission of a soft photon. Yeah. And so, for example, something like this. I could imagine attaching myself, adding a soft photon here. So this is my soft photon gamma. So actually, let me not draw it on here. So I'm going to draw it over here. Same process from alpha to beta, but now I add a soft photon. So I'm interested now in this amplitude. Amplitude of alpha to beta plus this soft photon, which I'm going to call gamma. And basically, Weinberg show us that this amplitude is related to that amplitude in a simple way in the limit that this photon is very soft. Again, I use momentum Q to denote that soft photon. Okay? And the argument is actually very simple. So he basically say the following. So let's say this momentum, let me call it Kn. N basically label the particles, right? K1, K2, K3, and here is Kn. So this leg is Kn. Because I attach this photon, this particular leg, the momentum conservation tells you is what? Do you agree? It's Kn minus Q? Yeah, momentum conservation. I'm drawing my arrow this way. So this is Kn minus, no, it's Kn plus Q, sorry. I did not do my sign. So this is Kn plus Q. Momentum conservation tell you now it gives rise to Q and Kn, no? So this virtual leg has momentum of Kn plus Q. And so, and we know how to write down that propagator, no? So we would say this must be roughly equal to that times what? Times, let's write down that propagator. That propagator would be Kn plus Q square plus the mass of this particle, whatever that is, square. And I'm going to label the mass of the particle by Mn because who knows? Each of these particles might even have a different mass. So I'm just going to Mn. You agree? Yes? And then if you want to keep track, there's an I epsilon here. Mostly we will ignore it. And then let's think about the numerator, no? What is the numerator? Well, I am emitting a photon, so that better be a polarization that specified the stage of the photon. So that's going to be a polarization, and I'm going to call it epsilon mu. That depends on the direction of the soft photon, something like that. This describes the polarization state. You tell me what is the polarization state you are interested in for that photon. You better put in there. And now to make all the indices contracted, because there's this mu, you have to contract it with something. And then Weinberg tells us, well, what can you contract with? You have the momentum, and this momentum and that momentum is basically the same because Q is so soft anyway. So you would say Kn mu. That seems like a fairly natural guess. Yes. And to make it as general as possible, as a Weinberg style, is to say, well, this coupling is related to the charge of this particle. So I'm going to call it E, but labeled by N, because who knows what that charge is? I'm going to call it En. Are you with me so far? And then finally, to keep track of sign, because your photon can be attached to an outgoing link or an incoming link, you can convince yourself this factor, there is an overall factor, I'm going to call it eta n, where eta n, it can be equal to +1, plus or -1, depending on whether that leg is incoming or outgoing, okay? And because this soft photon can be attached to any of these hard legs, so you should sum over all the n. So this is the relation. You got it? So this diagram with the emission of soft photons should be related to the original diagram without the photon times, this is called the soft factor. This is some soft factor. Any questions about this? You're good? Yeah? Okay, so this, by the way, let me make a comment already about this note. This actually look kind of like our soft theorems already, because this is some n-point function. This is some n plus 1 point function with the addition of the soft photon. You see what I mean? And if you think actually even further, the amplitude, if you use LSZ, amplitude is related to some kind of correlation function anyway. Although it's not the kind that we compute in cosmology. Those are called in correlation function because the state on the left and the right are the same. For scattering, we do in-out correlation function. But nonetheless, the schematic is the same. So an n plus 1 point function with a soft photon and an n-point function without that soft photon. And now basically here's what Weinberg pointed out. If Q is very soft, you can simplify the denominator of the soft factor, no? If Q is very soft, then what can we do? Let's expand it out. So we say Kn plus Q square equals Kn square plus 2 Kn dot Q plus Q square, of course. Yeah? But the denominator has plus m squared here. At the end of the day, Kn, that outgoing momentum has to be on shell. And because it's on shell, this is just 0. They add to 0. Yes? And if your photon is on shell also, you can just ignore this, or you can say, well, my Q is so small anyway, I'll be dominated by this term. Either way, that is what sits in the denominator. Does that make sense? And so the soft factor, is basically this, eta n, En, Kn, mu over 2Kn. Let me just ignore the epsilon, although I'll make a comment about that later. So that's it. That's the soft factor now. Any questions about this? Yeah? And this basically tells you the amplitude has this behavior. It actually has a pole in the soft limit. It goes like 1 over Q. Yeah? And by the way, the fact that it goes like 1 over Q, when you make it soft, the soft factor actually blows up, is the reason why when you add the soft photon, you can just imagine you add it to an external lake. If you add it to an internal lake, you are not going to have this enhancement of 1 over Q. It's important. We are using the fact that it's attached to the external lake so that this adds up to 0, because these are on shell. And so that is basically the form of the soft factor. So the main 2 comments I want to make is the following. One is that it goes like 1 over Q. And then the other is that what Weinberg actually go on to say, he said the following. He said, look at the photon polarization. You know, for the photon polarization to be physical, for it not to be pure gauge, A mu cannot be d mu of something, which means physical polarization cannot be something that's proportional to Q mu. Yes? Yeah? A polarization that's proportional to Q would be just pure gauge. Yeah? And so he basically suggests, point out that the soft factor, if you put this to be equal to Q mu, you should get 0. You should not get anything. So if you put it in a gauge mode, so we expect basically this sum, n, En, Kn, Kn dot Q, Kn dot Q, with the factor of 2 should be equal to 0 if you have pure gauge. Yes? And of course, if you do that, this soft factor now cancel. And now you recognize this statement. What is this statement? The fact that this is equal to 0. What is that? Huh? Charge conservation. So basically, this is his way of showing, actually, if you have this spin 1 gauge boson, this is how you can actually see charge must be conserved. Okay? Using basically amplitude arguments. Any questions about this? And then let me tell you about the spin 2 case just very quickly. Any questions about what I just said? That's his argument. Some of you probably have seen it. So the graviton case. No, the graviton case, you would basically say the same thing. I won't even bother drawing the diagrams again. It's basically the same over there. So you would say alpha to beta plus the graviton, let me call it G, has to be equal to this process times the soft factor. So now let's practice. Let's practice how we write down a soft vector. The denominator is always that combination, which if you go on shell, would go like 1 over q, would be proportional to q. So I'm just to go ahead and do that. Yeah? Let's think about the numerator. The numerator, you are trying to emit a graviton, and so you have to write down the polarization tensor for your graviton. It has 2 indices now. Yeah? Instead of one index. And so you now again ask yourself, how do I contract indices? And the only thing you can use, if you think about it, is the momentum of the hard particle. And so you say, we say Kn mu, Kn mu. Okay? You're okay so far? And again, as per Weinberg style, he's trying to be very general. Who knows what that coupling is? So that coupling constant of your particle with the graviton, let me call it G. And let me be super general. Let me make it dependent on n. So she's calling it Gn. Okay? And then we run the same argument. So once again, the point number 1 is this amplitude, just like the photon case, has a soft divergence of 1 over q. That is still true. And then the second observation is what Weinberg famously pointed out now. So you say, well, this graviton polarization tensor, I also do not want it to be pure gauge. If it's pure gauge, I should get amplitude 0. And so he said, if I just say pure gauge, would be proportional to Q mu, for example, or Q nu if you want. So that would be a pure gauge. And so you plug in that here, what do you get? Gn, Kn. If it's mu, the Q, let me just not skip steps. So I have this, and then I have this. Again, these cancel. This better be 0. You expect this to be true by gauge invariance. And now, what is this statement? What does this tell you? What do you think? What does that tell you? So the sum over, sorry, I forgot the eta. The eta is important. So the eta can be plus or minus 1, depending on whether it's incoming or outgoing. So let me put eta n here. Let me put eta n here. Okay? Plus or minus 1, depending on incoming, outgoing. Let's compare this against something more familiar. I hope you know what this is. If I ask you this, what do you expect this should be? It should be 0, because that's just energy momentum conservation. So you know this has to be true. And so for this, to respect that, you basically are forced upon to make the statement that, well, this must be universal. It cannot depend on n. In that case, you can just factor it out. Yes? And so you say, combining these two observations, you say Gn must be independent of n. So he proved equivalence principle, that the coupling to the graviton has to be universal for any particle you want. So he proved, so this is universal coupling. And if you want, the equivalence principle. Okay, so these are famous classic theorems. I feel if you haven't heard about it, you should at least hear about it. Any questions? Any questions? Let me make one final comment about this, and then we'll talk about black hole, maybe the beginning of it, okay? Let's look at the soft vector, this soft vector. I want to draw your attention to the fact that this diverges like 1 over q. Yeah. And it turns out you can make the following, draw the following physical implication about this 1 over q behavior. And I'm going to focus on time dependence. So I'm going to focus on the fact that the amplitude actually goes like 1 over frequency. What is the physical implication of that? So I want to talk a little bit about that. Okay. If you make the right kind of arguments, which I don't have time to make now, if you want, a very nice argument was made by this article by Ashok Sen about a few years ago. That tells you that there is some sense in which you can think of this part, even though it's just a soft factor in an amplitude. You can think of this part as, roughly speaking, a classical graviton field. So the soft factor roughly speaking, give you actually h mu nu. Indulge me for a second. If you have an h mu nu in Fourier space that actually look like this, h mu nu now in Fourier space for this very soft graviton with a 1 over q pole, which means in frequency goes like 1 over omega. Let's ask ourselves, what is the time dependence of this graviton? You understand my question? So I'm basically doing the following. I have a graviton. I am going to ask, how does it depend on time? And the way I do this is I'm going to do a Fourier transform back from frequency space or momentum space into time. And then I basically do this. Omega. And I want to know if I indeed have a graviton that in frequency space have a 1 over omega pole, what does it imply about its time dependence? Do you know how to do this? This is, of course, not well defined because you have to integrate this from, let's do it in complex plane. This has a pole right at the origin, and you are supposed to integrate along the real axis. So you have to give a prescription. How do you integrate around that pole? Well, fortunately, if you look at Weinberg's theorem, there is a minus I epsilon there. So let's do the minus I epsilon here. Now your pole is not on the real axis, but actually here. This is the I epsilon. And if you do these calculations, do you know what it is? I think you probably have seen this before. Do you know? What is this as a function of time? Does anyone know? It's a step function. Yes? Because if t is positive, then you have to close the contour up, you get a non-zero answer. If t is negative, you have to close the contour down, you get 0. Yes? So you know this is roughly the step function. So as a function of time, it looks like this. So it's 0, and then it goes like here. As a function of time, h mu nu as a function of time, it goes like this. So you might wonder what this is about. This is called gravitational memory. So this is telling you the following. Remember, we are actually doing the soft limit of the amplitude, which means really the Fourier or the momentum space answer should not just be this term. There are other things. Once you go to high omega, this is no longer the answer, correct? So really, the graviton, as a function of time, should have other things that contribute not as soft momentum, but as finite momentum or high momentum. Those things we have not included. If you have included those things, you might have found something like this. You would have found like what our experimentalist friends actually see in LIGO or Virgo is you see gravitational waves, but in the long run, in the very long run, because of this 1 over omega pole, you will see an offset that the gravitational h mu nu is, let's say, 0 before your LIGO event. But after all these waves are gone and so on, all this oscillation and so on, at the end, you should see this outcome. The fact that there is this offset is called gravitational memory. The connection between the soft factor and gravitational memory was first pointed out in papers by Schrödinger and collaborators. But I recommend this article by San, actually make it, it's fairly pedagogical. But that's the connection. So somehow, I have told you actually many different things about soft theorems now. No, soft theorem as in cosmology, correlation function, soft theorem in amplitude. Secretly, there must be some relation between them, because if you think about it, in the end, amplitude and correlation function are related. And furthermore, the soft theorem actually implied this kind of 1 over Q pole implies something about gravitational memory. What does it mean in practice? It means something like this. You have your LIGO detectors, you have these 2 mirrors, you have gravitational wave pass through, and so they oscillate back and forth. As you know, in transverse traceless gauge, freely falling particles, they stay at the same coordinate position. Yeah? And so after the wave pass through, they are staying at the same coordinate position, but now H has an offset, which means after the wave pass through, the net physical separation of the mirror has changed. If it's originally 1 kilometer, now it will be 1 plus a tiny, tiny, tiny 10 to the minus 20 kilometer. You see what I mean? There will be an offset. And in fact, people have plans or proposal to look for this gravitational memory. Any questions? Any questions? That's all I have to say now about nothing soft now. So, any questions? Yes.
So going from the correlation functions to the amplitude to vice versa, is it just through the LSE formula? Like correlation
It is the LSE formula, but there's one thing you have to be careful. In cosmology, the correlation function we are interested in are called in correlation function. We sandwich our observable on the left and right by the same state. Whereas in scattering, the correlation function that you use in LSE is actually there's some in and there's some out state. It's a different kind of correlation function. You have to keep that in mind. But other than that, yes, at least at some level, they are connected. Okay. Well, we have about 20 minutes to run. Should I start talking about black holes so that we actually have at least some discussion before the end, which will be tomorrow? Tomorrow will be our last lecture. Let me start off by telling you something about black holes, okay? And maybe just for 10 minutes. If you think about my strategy in cosmology, I decided to study something simpler. Instead of looking at the metric perturbation, let's just think about a scalar field living, a spectator scalar living in the cosmological background. It turns out for black holes, you should do the same. So instead of thinking about metric perturbation around a Schwarzschild background or a Kerr background, which I'm going to show you the equation. Let's start off just by thinking about a spectator scalar living in a Schwarzschild background. It turns out you learn a lot just by thinking about that already, yeah? And so that's our strategy. So consider this. Again, I use phi a lot. This phi is just some other scalar field, okay, that live now in a Schwarzschild background. This box is the Schwarzschild background, which is, let's just remind ourselves, is this one. L square. Okay. You know that's the Schwarzschild metric. Yes. And we should just write down the equation of motion for this scalar field. So this is a scalar field. Forget the fact that it could gravitate. It's like a spectator living in this background. And I'm setting the mass to 0 because it turns out the massless case give you the most direct kind of analog to eventually the metric perturbations. Okay? So massless scalar in a Schwarzschild background. And I think you all know how to write down this equation. Yeah? And I was going to originally give this to you as an exercise, but in the interest of time, I'll just tell you the answer because I assume you can do it anyway. So let me tell you the expression, if I can find the expression. Apparently, I've lost the expression. How come? There you go. Okay, so let me try to write it in a way that is useful for us later. I'm going to write this way. Sorry, the R. There's this part. This pertains to the radial derivatives. I hope I didn't mess up. The time derivative now, because of the way I shuffle the factor, is just dt squared. And then finally, there is this part, which is plus I'll just write this as the angular Laplacian. I hope you understand what that means. Acting on phi equals 0. So this is the angular. This is the Laplacian on the two sphere. Okay? I hope at least this looks kind of plausible. You would get something like this if you do the work. I urge you to at least do it once yourself. Just take this and deduce this. Okay. Our next step would be to do the usual. We have a linear equation for phi, so usually we do separation of variables. Yeah. In cosmology, we do e to the I omega t, and then we do e to the ikx, because e to the ikx plane waves, because we have spatial translation, right? Here, because of the black hole, we don't have spatial translation anymore. The only thing left is rotation. And so if you want to do separation of variables, the natural thing to do would be to say, yes, e to the minus I omega t, that's good. But the angular part, you probably want to do YLM, theta phi. Yeah? And then there will be some radial function, and I am going to call it phi Lm, because the radial function is going to depend on Lm as a function of R. Really, it should be a function of Lm and omega, but I'm going to skip that. You got that? And of course, your most general solution should be a superposition of all these for different omega, L and M, yeah? But I'm going to only focus on this mode. We can do it one by one, yeah? If you take this and go ahead and plug in, I hope you know, you just tell me. If I take this and plug in, what is the equation for YLM? What happens to the dt square? Becomes omega square, okay, very good. So this is plus omega square. How about the Laplacian square, the Laplacian, angular Laplacian? Becomes, acting on YLM, I hope you know. You might not remember the sign, but it's LL plus 1. Turns out there's a minus sign. Yeah? Okay? So this is the equation. So let me clean this up a little bit. So there's a minus sign, L plus 1, phi LM equals 0. Let me make a comment about this already. So in general, of course, this radial function could depend on M, yeah? But if you look at this equation, the operator that acts on it doesn't care about M. It only cares about L. And the reason is because your background is rotationally symmetric. And so from now on, I'm going to be lazy and just actually even skip this M label. Although in principle, this coefficient, of course, you are free to choose coefficient that varies with M. But as a mode function, it doesn't care about M because of spherical symmetry, okay? And so this is now the equation that we are supposed to study. And the nice thing about this equation is now is not a PDE as usual because we do separation of variables. It's an ODE, a second order. And now we just have to study this. Any questions about this? And then I'm going to write in a form that's convenient for thinking about it. And then I'll tell you what we are going to do with this form, and we'll do that tomorrow, okay? Any questions so far? Any questions so far? Okay, so it turns out there's a very useful radial coordinate that you can define that can make this equation simpler, and it's called the tortoise coordinates. So if you look at the spatial part of the metric, the non-angular part of the metric, you can see you have basically this overall factor minus dt square plus dr square over 1 minus rs over r square. Plus angular part, which I'm not going to write down. But look at this part. It turns out it's useful to define a radial coordinate so that the speed of light in that radial coordinate looks like 1. And so you define a radial coordinate, I'm going to call it the r star square. This is just a definition, no? Which clearly you can do. You just integrate this to find r star, no? And if you write down r star, this is what r star looks like. If you do the integral, and you should check, is r plus rs log r over rs minus 1. It looks like that. Okay? You should check it. And this coordinate becomes useful, again, as what I said. It makes the causal structure kind of simple because now this part of the metric, other than this conformal factor, it looks like flat. dt and dr star, the relationship look kind of like flat space. And tell me where's the horizon in r stars? The horizon, which is, of course, r going to rs. Rs is the Schwarzschild radius. When that happens, r star goes to what? Minus infinity. So you have stretched the horizon from the Schwarzschild radius all the way to negative infinity. And then spatial infinity, R go to infinity, R star also go to infinity. Because this is just a log, okay? So this is what you should remember, okay? Now my horizon look very far away now. It's like minus infinity, okay? In this R star coordinate, okay? My claim is if you use this R star, you can simplify this enormously. The equation, box phi equals 0, imply, and then I'll just make a few comments, and then we'll continue tomorrow. The equation looks like this. The R star square plus omega square L plus 1 R square minus L, sorry. Did I do this wrong? Yes, plus Ls over L cube. This whole thing acts on actually not phi, but R times phi, turns out. R times phi L equals 0. Okay? This is this now becomes the equation. And this is a nice form of equation to look at for reasons that I will now explain. Any questions? I hope at least you can imagine yourself doing this, checking this. So this is my homework for you. Check this too. Yeah? Okay. Notice actually we did something very similar in cosmology. In cosmology, instead of phi, you remember I introduced a psi that turns out to make things simple. Here it turns out you multiply by r to make it simple somehow. Okay. Why do we like this form of the equation? Look at the structure. I have something like second derivative, spatial derivative, square acting on some field. And this part you can think of as if it's some potential. You can think of it as a function of r. You can think of it as a function of r star. That's up to you. R and R star are related anyway. Yeah? Yes? There's some potential. The reason why we like to write it this way is because now it looks like you're solving Schrödinger equation. Yes? Second gradient minus a potential acting on your wave function equals 0. Yes? That looks very familiar, right? And to understand now how to apply this, let's draw what this potential looks like. And the form, I think, tells you. Can we do it together? So R star is the x-axis. The potential is like this. Tell me, the potential far away at large R, what is the limit? Goes to 0. I hope you can see that. Yes, at large R, it just go to 0. So far away is 0. How about at the horizon? When R is approaching the Schwarzschild radius Rs, it also what? It also go to 0 because of this factor, no? Actually, sorry, I should remove. Let me not include the omega here. Sorry about that. Well, let me include it, but let me say I'm plotting this for omega equals 0 for now. Okay, let me do it that way. Okay. So if I set the omega to 0, just ignore it for the moment. This is going to 0, so the potential looks something like this. In fact, you know what? I think a better thing for me to say, just to make the quantum mechanics analogy as perfect as possible. Let me do the following. I'm going to call this part the potential. This is minus V R star, in which case I don't even need to talk about this. And then this equation now looks like this. The R star square minus the potential acting on my wave function, so to speak, equals, I'm going to put the omega square on the other side, minus omega square alpha. You see what I mean? So this now looks like the time-independent Schrodinger equation. Yeah, this is the Hamiltonian or the negative thereof. This is the energy eigenvalue. Okay, this is probably a better way of writing it. Let me do that. Now the potential vanishes at the horizon. This part, the potential vanishes at the horizon and vanishes at infinity, and you can convince yourself it has a peak somewhere. And if you check, this peak is at around 3 GM. Okay? It's not exactly that because it depends on L, but it's not too far from that. Around 3 GM. Okay? Any questions about that? And then the rest of our task, which we will not do today, is to think about how this behaves when I apply to it different boundary conditions. So let me tell you those boundary conditions, if I may, and then I'll really let you go. Any questions? So here's the applications. I'm going to list quite a few, but I will only talk about one tomorrow, okay? So number one, you know what happens when you have two black holes and they spiral each other in a binary and eventually they merge. After you merge, you would have a bigger black hole that's initially very perturbed, yeah? And in fact, it's like a bell. It rings, it oscillates, and the oscillation eventually damp down, and then it quiet down to the final, usually rotating curved black hole. Yeah. I can study the perturbations around this final black hole using an equation like this. Of course, not exactly this equation. This equation is just for a spectator scalar in a Schwarzschild background. But my claim is if you work out the metric perturbations of this ringing black hole around a Schwarzschild background, you will get an equation that looks very much like this with a potential that's slightly altered. In fact, I can even tell you that potential. Instead of plus Rs over R cubed, you're minus 3 Rs over R cubed. That's it. That's the only difference for a Schwarzschild black hole. Very small difference, okay? But imagine you now have that equation. Now you can use this equation to study this ringing, the ringing of the black hole. And this ringing, in particular, you are interested in this kind of solution. You have this potential. So this is called ring down a black hole, where you have this potential, B R star as a function of R star. You will be particularly interested in certain modes. The modes that escape to infinity is a wave that can travel to the observer. Think of these perturbations as basically the graviton, right? Gravitational wave that you can eventually observe. And at the horizon, these modes should just fall through the black hole. They get absorbed by the horizon. If you impose these kind of boundary conditions, outgoing at infinity, ingoing into the horizon on the other side, this is where the horizon is, I should say, right? Because this R star going to negative infinity, and this R star going to infinity, far away. If you impose these kind of boundary conditions, you can check, based on your intuition about Schrodinger equation, that these omega, the energy eigenvalue, they are quantized. Only certain energy eigenvalue are allowed. Only certain omega are allowed. And furthermore, you can check this is complex. Turns out this frequency is not a real number. It's complex, which means these modes, you look at the sign, they decay. These are called quasi-normal modes. And the fact that decay is very intuitive because you have some fluctuations in the aftermath of the black hole, and it can be very complicated. But these fluctuations are losing energy at infinity and into the horizon. So the amplitude has to decay, basically. And so once you impose this boundary condition, you can solve for the omega square energy eigenvalues. You will find the quasi-normal spectrum. These are called quasi-normal mode because they are not normal. Normal would mean frequency is real. Because they are complex, they are quasi. And so if you look at the LIGO data, you will see the in spiral merge, and then after merging, kind of oscillations that actually decrease with time. So this decrease, this damping is because omega has an imaginary part. And you can find that spectrum by basically solving a Schrodinger equation, just imposing that boundary condition. You got it? So that's the first application that you can think about. Second application, you can think about, I'll just mention second and then I'll mention the third. That's it, okay. The second application is the following. Is one of those fun situations where you consider now not the metric perturbation but a scalar field that live in the black hole background. But now let me have the scalar field actually have a mass. Let me turn on a mass. And then it turns out you will find the following interesting situation. You can consider a scalar cloud around the black hole where this cloud goes to zero far away. It's like a hydrogen atom. So you say phi go to zero far away. You impose that boundary condition. And then at the horizon, the natural thing to do is to impose regularity of the field at the horizon. But it turns out if your black hole is spinning, it turns out effectively what happens is you can actually pull stuff out of the black hole. So the boundary condition is like this, going to zero far away. If the black hole is spinning with just enough angular momentum, there's a way to grow this scalar cloud around the black hole and extracting energy and angular momentum off the black hole. And that is called superradiance. This is called superradiance. When this scalar has a mass that's non-zero. And again, I want to say conceptually, you are really looking at a similar kind of equation, but you're studying a different boundary condition. In this case, spinning black hole background, scalar mass non-zero. You can actually grow a cloud, and as you might be aware, this is actually one of those bounds that people put on light dark matter, basically, or it doesn't even have to be dark matter as such, because this cloud can just grow as long as there's some initial amount, you can grow superradiance. And lastly, I'll just end here and I'll elaborate tomorrow. Lastly, you can use this equation to study tidal deformation. So I'm going to draw the potential again, the tidal deformation. So imagine you have a black hole. This is your black hole. But imagine there's some star around it or another black hole around it. It would generate a gravitational field, like so, generate some gravitational field that act on this black hole. And you will be interested in asking, well, does this tidal field causes tidal deformation on the black hole or not? Just like if this were the Earth and the moon, you would say the moon's tidal field can distort the shape of the ocean around the Earth, no? You can ask a similar question. Does this tidal field distort the black hole? How would the black hole respond to a tidal field? And to answer that question, you solve the same equation. You look at that equation, you impose now far away, you have this tidal field. So this is your gravitational perturbation, I'm just going to call it phi. You have this tidal field from far away, and you ask, if I impose regularity at the horizon, what kind of response do I get? Does the black hole become this and generate its own multiple response or not? If it generates a multiple response, it would cause basically a tidal tail. I'll talk about that tomorrow, but this is the third application. The main thing I want to get across is this equation, you can use it for many things, and the different application is all about choosing different boundary conditions, really. Yes? So tomorrow we will only talk about one, we'll talk about tidal deformation. All right? Thank you, everybody.